Hey everyone, and welcome to this explainer. If you're working in the clinical or graduate genetics space, you already know that interpreting genetic data is, hands down, one of the most critical and, honestly, complex tasks in modern medicine. Today, we're zeroing in on a massive turning point for the field, the 2015 ACMG/AMP guidelines. This framework was absolutely a monumental shift. It pulled us away from those old, ad hoc, individual interpretations and gave us a systematic, highly structured, evidence-based methodology for evaluating sequence variants in Mendelian disorders. It's literally the rulebook that changed everything.
Okay, let's dive into this and look at our agenda for today. We're going to start with Part 1, the Variant Interpretation Challenge. Then move to 2, the 5-tier hierarchy. After that, 3, weighting the evidence. 4, the combinatorial logic engine. And we'll wrap up with 5, clinical impact and caveats.
Let's kick things off with Section 1, the Variant Interpretation Challenge. To really appreciate this framework, we have to understand the massive paradigm shift that forced it into existence in the first place.
And that brings us to the ultimate question. How do we achieve diagnostic consensus in the era of next-generation sequencing? Because, high-throughput NGS completely revolutionized what we can do. But with the rapid adoption of large gene panels, exomes, and whole genomes, clinical labs are just getting hit with this massive, overwhelming influx of novel sequence variants. It's like drinking from a fire hose. The complexity is staggering. So, if multiple labs are looking at the exact same genetic sequence, how on earth do they actually agree on what's causing a patient's disease?
Well, the very first step to getting everyone on the same page is establishing a precise, shared language. For decades, the genetics community was operating in a bit of a Wild West when it came to terminology. We tossed around words like mutation and polymorphism all the time, but those terms are actually a big problem because they carry baggage. They lead to these automatic, incorrect assumptions. Like people just assume a mutation is inherently pathogenic and a polymorphism is inherently benign. The ACMG guidelines say absolutely not. We have to abandon those outdated terms. Instead, we use the standardized, completely neutral term variant. And because variant is neutral, it forces us to attach a modifying classification to actually give it clinical meaning.
Which leads us perfectly into Section 2, the 5-tier hierarchy. Let's look at the target output of this entire framework.
Here is that 5-tier hierarchy. This is where our entire clinical investigation ultimately has to land. Every single piece of evidence we dig up is directed towards sorting a variant into one of these 5 specific buckets: pathogenic, likely pathogenic, uncertain significance, which we usually just call a VUS, likely benign, or benign. This top-down hierarchy is the absolute end goal of our analytical process.
So the crucial point is how we define the word likely in a clinical setting. Obviously, pathogenic and benign imply near absolute certainty. But what does likely pathogenic actually mean in practice? Well, the framework specifically defines likely as having a greater than 90% certainty of a variant being either disease-causing or benign. Now, you might be thinking, okay, 90% is a somewhat arbitrary boundary. And it is, but it's also incredibly critical. It sets a standardized threshold so clinicians and patients know exactly what they're dealing with, allowing them to tolerate a very slight, less than 10% chance of error while still confidently moving forward with medical decisions.
All right, Section 3. Weighting the evidence. We know our final destination, so how do we actually get there? Let's look at the foundational evidence categories that feed this whole system.
The golden rule here is we never, ever rely on a single data point to make a diagnosis. Instead, we're pulling distinct inputs from a few major streams. First, population data. Like, is a variant simply too common in the general public to be the cause of a super rare disease? Then we have computational or in silico predictive models. We also look at functional data from established lab assays. And finally, segregation and allelic data, checking things like if the variant arose de novo in the patient or how it tracks through a family tree. It's the aggregate of all these categories that matters.
And here is how we organize that aggregate, the evidence framework matrix. On the right side, we've got criteria supporting pathogenicity. And over on the left, criteria supporting a benign impact. But notice how the evidence isn't just grouped by type, it is rigorously weighted by strength. Very strong, strong, moderate, and supporting. Every piece of evidence gets assigned a specific alphanumeric code. So, for example, if you have a predicted null variant in a gene where loss of function is a known disease mechanism, boom, that earns a PVS1, pathogenic very strong 1. But, say, a variant is just absent in a large population database, that might only give you a PM2, pathogenic moderate 2.
Okay, Section 4, the combinatorial logic engine.
Once we've gathered our weighted P codes and B codes, we need a way to process them. Enter the engine.
And this brilliantly illustrates the whole concept in one view. It's basically a giant balance scale. Over on the far left, you have the raw databases and experimental evidence being categorized into those weighted P codes and B codes. Then, in the center, we drop those weights right onto the combinatorial logic scales. We are quite literally weighing the pathogenic evidence against the benign evidence. And finally, on the far right, depending entirely on how that scale tips, the engine spits out our definitive 5-tier clinical assertion.
So if you're a laboratory geneticist, this is your exact step-by-step workflow for building a scientific case. Step 1. Mine the clinical records, the literature, and the population databases. Step 2. Evaluate that raw data and assign your weighted codes. Step 3. Apply the framework's strict combinatorial logic rules. And Step 4. Generate a report with that final 5-tier clinical assertion.
Let's look a little closer at how those logic rules actually operate. The beauty of this framework is that it completely strips away subjective guesswork. It gives you explicit mathematical combinations. So, to reach a definitive classification, you might combine one very strong piece of evidence, a PVS1, with at least one strong piece of evidence. The result? You've got a definitive pathogenic classification. Or, alternatively, that same PVS1 combined with two moderate pieces of evidence. Same result. But look at the row below that. If you only have one very strong and one moderate piece of evidence, you haven't quite met the threshold for pathogenic. You objectively land at likely pathogenic. It's just a wonderfully elegant, reproducible system.
Moving on to Section 5, Clinical Impact and Caveats. Because, look, this isn't just some abstract academic exercise in logic. We have to bring this firmly back to the real world, back to patient care and clinical responsibility.
The clinical stakes here are astronomical, and the guidelines are crystal clear on this. A variant of uncertain significance, or VUS, should absolutely not be used in clinical decision-making. Remember that 90% certainty threshold we talked about earlier? It matters, because calling a variant pathogenic or likely pathogenic triggers actionable, real-world medical steps. We're talking about altering treatments, starting aggressive cancer surveillance, or testing family members. But a VUS, that just means the scales haven't tipped yet. We need more data. Medically acting on a VUS can literally lead to unnecessary and potentially harmful interventions.
Now, what's really interesting about this slide is understanding the hard boundaries of the framework. You have to know where these rules do not apply. This system was designed primarily for Mendelian disorders with well-established gene-disease associations. You can't just slap these exact rules onto a gene of uncertain significance found in a broad exome scan. It's also not meant for somatic variants found in tumor profiling. Those need a totally different set of rules for things like treatment responsiveness. And it for sure isn't built to interpret complex, multigenic risk alleles for common stuff like type 2 diabetes or coronary artery disease. Context is everything here.
So we've seen how the ACMG/AMP framework took variant interpretation from a subjective art form and turned it into an objective, rigorous science. But the field is moving at lightning speed. As our functional assays get even more precise and our computational models are supercharged by massive new data sets, we really have to ask, how close are we going to get to 100% diagnostic certainty on that balance scale? Will the uncertain significance tier just eventually disappear altogether? It's an incredibly thrilling space to watch evolve. Thanks so much for joining me on this explainer, and keep questioning the evidence.